Okay, let's summarize this again. A change in current in a wire causes a change in magnetic field about that wire. The change in magnetic field results in a change in magnetic flux in coils within that field. Therefore, when a current in a coil changes, it's going to induce an EMF in the same coil. It's going to induce an EMF in other coils if there are other coils nearby, but it's going to as well induce an EMF in that same coil. Thus, we have what we call self-inductance. The induced EMF is given by this expression. E is minus L di dt, or delta I delta t, where L is called the inductance of the coil, and the unit for L is the Henry when we use volts for E, amps for current, and seconds for time. For this reason, this inductance, we call the coil, under these circumstances, an inductor. And inductors are an important component of electronic circuitry. We use them quite a bit. Now, in real life, inductors might look like this. This is one type, something where actually the coils are hidden, so it might look somewhat like this. This is like sometimes inductors, you make them yourself if you have the core. This is another inductor. One might ask, what is the expression for the inductance? When we developed the idea of self-inductance, you might have guessed it. But anyway, if my coil has n loops, and if phi is the flux through one loop, remember this expression that we wrote, n times phi is equal to L, the inductance, times I, which makes L, just isolating L, n phi over I, and then plugging in B times the area for the flux, so it becomes, so this is B times A, so that's the flux, so NBA over I. And then if my coil is like a solenoid, so it's going to be like this. So like a solenoid, that would be something like this. So if we plug in B in here, what we are going to get then, this expression, L is N mu 0 N I A over I. Notice that the I's cancel. And my inductance is given by mu 0 N, big N, capital N, times A. This is again assuming that we don't have a core. If we have a core, we have to add a kappa there. Notice also we have lowercase n and capital case N. Lowercase n is the total number of loops in the solenoid. Lowercase n is going to be the total number of loops of the solenoid over the length of the solenoid. So if we kind of try to get rid of having two expressions like that, and if we call the length of the solenoid small l, we can write this expression and plug it in here, then the expression becomes mu 0 n squared, length of the solenoid A. Remember, n squared, lowercase, means the number of loops per unit length. And again, if I have a core, I need to multiply this by kappa. So that's the expression for the inductance due to a solenoid that has, due to an inductor that has the shape of a solenoid. You know, of course, if the shape is going to be a little different, something like this, in this case, we have a ferrite toroid, you know, that circular thing like that. So in this case, the expression is, as you see it here, mu 0 kappa A n squared over L. Now, of course, like we just mentioned, the equations are going to depend on the shape of that particular inductor. So we have cylindrical air core coil, straight wire conductor. We can speak of an inductance due to a straight wire, etc. Multi-layer air core, flat spiral air core. You can go to these websites and find other expressions if you want to. Notice here, instead of kappa, they are using mu sub r, relative permeability of the core material. So that's what we are using in our case as kappa. So it's the same thing, the same quantity. Now, let's discuss this a little bit. Now, if we have in this case, we are asked to compare the inductance of two solenoids, which are identical except that solenoid 2 has twice as many turns per meter as solenoid 1. What's the relationship between them? L2 equal N1, or twice L1, or 4L1. Okay, if we remember the expression, it's mu 0 n squared LA. The expression is mu 0 n squared LA. N is the number of turns per meter. So if I double it, since it is squared, I quadruple it. So this is my answer. Since the inductor is going to store magnetic energy, even though temporarily for a very short time, one might ask, what's the value of the energy stored in an inductor? Okay, in this case, I'm not going to go through the process of showing you how do we get to it, but the energy stored is 1/2 of Li squared. It's a very similar expression to the expression that we had for the energy stored in a capacitor.